we will discuss on suspended growth system, that is aerobic system in which microorganisms are suspended in bulk of the liquid media. We will discuss certain basic fundamentals which are applicable for suspended growth system. Amongst the suspended growth system, activated sludge process is most widely used system, and today we will discuss the fundamentals of these systems in context of the activated sludge process. The modifications of the activated sludge process. So, in the context of activated sludge process, let us understand the basics of the working of the suspended growth system. Before we go into the details of the process, let me introduce you some of the basic terms which are used in context of the activated sludge process. Typically, the activated sludge process consists of a tank filled with the wastewater, where the wastewater or sewage enters and leave this tank, and within this tank we have very high concentration of microbial biomass, and the incoming wastewater gets attacked with these microorganisms for the consumption of BOD. So, all soluble form of BOD is consumed by these organisms, and in the process of consumption, part of the BOD is converted to CO2, which is released into the atmosphere, and remaining part is used for the further formation of biomass, which goes out of the system. The entire system is kept under mixed condition by use of aerators, either surface aerators or bottom diffuse aerators, either of these methods, which also helps not only for the mixing but also supply of excessive oxygen. So, this particular portion of the activated sludge process is known as aeration tank. So, in the aeration tank we have very high concentration of microorganisms under mixed conditions. They are suspended in the water, that is why it is a type of a suspended growth system. Now, in the context of this aeration tank, let us understand these terms. First is feed rate. Feed rate is nothing but the discharge of the wastewater, which is equal to liquid volume in terms of liters per hour. Volume can be expressed in terms of liters per hour or cubic meter per hour or anything of that sort. So, volume per unit time. Whereas, there is another term called dilution rate, and I can denote this by symbol D. Dilution rate is the rate at which the microbial biomass is getting diluted, or in other simple words, the feed rate as a function of volume of the vessel gives the number of volume exchange per hour. Okay, so let us consider this as the volume of the tank and the amount of the microbial biomass as symbol X. So, dilution rate is how much volume of the fresh wastewater expressed in terms of meter cube or liter, either way, is getting replaced with per cubic meter of the volume of the tank. Suppose if this much quantity of sewage is entering, this much quantity of sewage is getting washed out, because it is a continuous flow reactor, and this particular volume is how much percentage of the total volume, that is how much volume of the aeration liquor is getting replaced. So, it is its unit, of course meter cube gets cancelled out. So, its unit remains as per hour or per unit time. So, dilution rate is nothing but rate at which the volumes are getting exchanged. Now, if there is an existing bacterial biomass in the reactor, then it is also get washed out at a rate equal to dilution rate into X. To give you an example, suppose X is the total amount of the biomass in the system, then this biomass is getting replaced with the incoming fresh wastewater, which may have negligible biomass, and it is now coming out, which carries with it the concentration of the biomass. So, the concentration multiplied by the dilution rate gives the washout rate of the bacterial biomass, and this can be expressed as minus dx by dt. The symbol minus means it is getting diluted or getting decreased. So, the rate of change of bacterial biomass in the aeration tank is equal to dilution rate multiplied by concentration of the biomass in the system. Similarly, we have seen that from the monodes curve that the microorganisms grows within the system if they are supplied with the food, and this, suppose if mu is the specific growth rate, so the rate at which the microbial biomass grows in the system is equal to mu into x. So, the net growth rate can be called as dx by dt is equal to mu x minus dx. From this equation and this equation, we say that the net rate of growth of microorganisms is equal to specific growth rate into the bacterial biomass minus dx into x. So, this is the net growth rate of microorganisms. Now, why this particular concept is important? The importance of this concept is we have to have in the aeration tank very high concentration of microorganisms, because if we look at the fundamentals of the development of this system, we are intending to say whatever the microorganisms is present in 20 to 50 kilometer stretch of the river, we want to maintain it in a very small volume. So, we have to grow microorganisms. So, efficiency or the process of the activated sludge process depends upon the presence of active or viable microorganisms, and therefore, the growth rate of these microorganisms is of immense importance to us. So, the growth rate of the microorganisms depends upon the specific growth rate, which is a function of original biomass minus dilution rate. In a continuous flow reactor, now I am showing you again, suppose this is the aeration tank under mixed condition, wastewater is coming in, wastewater is going out, it has a particular volume, it has some initial biomass concentration in the tank, it is getting feed at the rate of q liters per hour. So, in this particular system, and say initial BOD I am denoting with a symbol S0, that is the initial amount of the BOD or food coming into the aeration tank. Now, if we want to grow the microorganisms, what is required? From the monodes curve, we need to increase the total food supply. Food supply, that is S, is equal to discharge into the concentration, that is discharge is in terms of meter cube per hour, concentration is in terms of kg per meter cube. So, total amount of food is nothing but kg per hour. So, how much amount of the food is coming is equal to discharge into substrate concentration, which in this particular case is S0. Now, the wastewater has certain fixed volume of BOD. Therefore, if we have to increase the growth rate of microorganisms, what we need to do? We have to increase the discharge rate, that is we have to allow more amount of the wastewater going into the aeration tank for a given volume. So, therefore, then only the S will increase. Once the food supply increases, the growth of microorganisms also increases. So, as the growth of microorganisms increases, we will have more amount of the, if you take the equation that we have just written, more is the specific growth rate, more is the amount of the growth of the organisms within the aeration tank. Now, on the second aspect, if we increase the discharge rate, what we are doing? We are increasing the dilution rate, because dilution rate is nothing but discharge per unit volume. Volume of the aeration tank is fixed. So, what we are doing? We are, by increasing Q, we are increasing the dilution rate, which means that in the net growth rate, if this is the equation, to increase the bacterial biomass, we are increasing the discharge. By increasing the discharge, we are increasing this as well as increasing this. As a result, there is no net change in the bacterial biomass. That is, if the system will attain a kind of a dynamic equilibrium where the growth rate is equal to the dilution rate. That is, there is no change in the biomass concentration. That is, dx by dt is equal to 0. So, the question comes, how to increase the biomass? Because one way to increase the biomass is by increasing the food supply, by increasing the discharge for a given volume, but that will also result in the increase in the dilution rate. So, there is no net growth. Rather, on the other hand, we have seen that Monod's equation becomes asymptotic towards the x-axis, which means that after certain stage of food supply, there is no net increase in the growth rate. So, in fact, if we increase the discharge rate beyond a certain level, rather what we will have net decrease in the bacterial density. So, if I plot a graph between dilution rate versus bacterial density, I am denoting with the symbol BD, bacterial density, there is a fast washout of the microorganisms. So, the entire discussion I am repeating again in the context that first of all we have to increase the microbial population in the aeration tank. To increase the microbial population, we have to increase the supply of food. Concentration of BOD in the wastewater is more or less constant. So, we have to increase the discharge rate for a given volume. By doing so, though we are giving opportunity for microorganisms to grow, but also giving more dilution. The net effect is that there is no net growth of microorganisms, but rather after some stage there will be washout. So, question comes, how to increase the bacterial population? To do that, what we do a slight modification in this process. What we do is, this is a continuous flow through aeration tank filled with water which has some bacterial biomass, and what we do, we introduce a settling tank which is known as secondary settling tank or secondary clarifier. So, we allow the bacterial biomass to pass out. Once they pass out, they enters into the clarifier where they get settled to the bottom. Once they get settled to the bottom, what we can do? We can recycle part of these organisms or biomass back into the aeration tank. So, what I am showing you with the top arrow is the flow line of water, that is, this is the treated water. All the BOD, soluble BOD gets converted to CO2 or the bacterial biomass. This bacterial biomass is captured over here, and part of this is recycled back and remaining part is wasted. So, this is the recycling of the sludge which we do in the aeration tank. That is why the process is known as activated sludge process. The word activated sludge process means we are running this process with the use of sludge which is highly potent for the degradation of organic matter, because these are the organisms which has grown, we are bringing back into the system, and hence we are increasing the bacterial concentration. So, question comes, how this bacterial concentration is getting increased? Let us take the example. Suppose the yield factor of this, now remember the yield coefficient. Yield coefficient is amount of the biomass produced per unit amount of the BOD consumed. So, suppose for a given yield coefficient we get say 0.5 kg of biomass per day, which means that for a given level of BOD and supply, this system is able to produce 0.5 kg of the biomass. This 0.5 kg every day it is getting produced, every day it is getting washed out. So, there is no net growth of microorganisms in this type of a system, that is 0.5 produced, 0.5 going out, 0.5 produced, 0.5 going out. So, there is no net growth of the organisms. This is a flow through process. In this particular system, which is a configuration of an activated sludge process, what is happening is 0.5 kg produced, it is getting washed out, trapped over here, we are giving back 0.5 back into the system. Now on the second day we are having 1 here. So in case if I plot a graph between say time in days versus biomass in terms of kg, so on the day 1, 1, 2, 3, 4, 5, 6 and so on. So these are the number of days. On day 1 we are able to produce 0.5 kg. So on this axis I am showing writing 0.5, 1.0, 1.5, 2 and so on. So on day 1 we are producing 0.5. Now if the system is flow through type, what will happen on next day? We will produce 0.5, we will wash out 0.5, so there is no net change. On the day 3 we are producing 0.5, we are also wasting 0.5, no net growth. So the nature of the curve for the flow through type of a system, that is system 1, will be like this, that is aeration tank will only have 0.5 kg at any given time, and after that there is no net growth. But by recycling the sludge, what we are doing, we are producing 0.5 at the end of the day 1, at the end of the day 2 what we are doing, we are producing 0.5 and recycling back 0.5, so net biomass becomes 1. On day 3 it becomes 1.5, on day 4 it becomes 2, and this is the level. Suppose if we want to have the biomass concentration in the aeration tank, from the 5th day onward we can start wasting the biomass from the sludge line, and then we can have the graph like this. So this is how we are artificially increasing the biomass concentration in the aeration tank. That is why it is known as activated sludge process, which consists of an aeration tank where very high concentration of bacterial biomass is suspended and they are artificially increased by recirculating part of the settled sludge back into the system. So this is broadly the functioning of the activated sludge process. So always remember, when we say activated sludge process, it consists of an aeration tank followed by a secondary settling tank and a sludge recycling line and sludge wasting line, treated water effluent line. This entire system, aeration tank, sludge recycling line and secondary settling tank, together is called activated sludge process. So having understood the basic working of the activated sludge process, question automatically comes that how much amount of the bacterial biomass should be there in any process, or how the system self regulate itself for change or fluctuations in the BOD concentration. To illustrate the point or the question which I had just raised is, this is the aeration tank, wastewater is coming, wastewater is leaving out of the aeration tank. This aeration tank consists of aerators, bacterial biomass, then we have secondary clarifier. From the secondary clarifier the treated effluent goes out, settled sludge, part of the settled sludge is recycled back into the system. So the question is how much recycling we should do, and that depends upon how much amount of the bacterial biomass we should have in the aeration tank. So this is question number 1, that is amount of the biomass. Second question comes, which is important, is the BOD which is coming in the wastewater is never constant, because a sewage or any industrial wastewater always fluctuates in any of its characteristic parameters. So because of the fluctuation in the concentration, how can we ensure that the treated BOD, the effluent in the treated water, the BOD should be less than 30 milligrams per liter. So this is the second question, that is self regulation of the system. So we will understand how these two concepts simultaneously. Like the example of with the graph, I had mentioned that assuming that 0.5 kg of biomass is produced every day, so we keep on recycling the things till we achieve a certain level of desired biomass. So The question is, that is question number 1 is, how much is the desired level of the biomass? That depends upon the food to microorganisms ratio or organic sludge loading rate that we want to maintain in the system. How do we do it? First, let us consider the case that this is the graph between the amount of the biomass in terms of organic sludge loading rate starting from 0, 0.1, 0.2, 0.3, so on till 0.7. And on this axis, if I show relative degradation capacity. So, in terms of percentage, when there is 0 biomass, 0 degradation. As the biomass concentration increases in percentage terms, the degradation capacity of the system also increases. So, here what is happening is, if we see organic sludge loading rate of food to microorganism ratio is nothing but BOD, soluble BOD divided by kg of bacterial mass. That is, if I draw the analogy which we had done it previously, that for a given level of food, if we have number of organisms, the food will be consumed very fast. As the number of organisms increases, the consumption of or rate of consumption of food increases. As the number of organisms decreases, the rate of consumption decreases. That is, as we keep on increasing the microbial population, the degradation capacity also increases. Now, the BOD of the wastewater is coming. So, F by M ratio, at low F by M ratio means very less amount of food and very high microbial population, because food to microorganism, lesser is the value of F by M, means for a given amount of food we have very high level of microorganisms. So, in that case we are actually operating at a very low degradation capacity, and as the concentration of food increases, the degradation capacity of the system increases, and it increases like this. So, up to by the time we reaches to 0.7, the system is almost operating at a 100% degradation capacity. So, it follows a somewhat like this curve, that is, initially as the F by M ratio or food to microorganisms ratio or organic sludge loading rate is less, we are operating at a less degradative capacity. As the F by M ratio, as the supply of food increases, the degradative capacity increases. After that, further increase in the F by M ratio will not result in any further increase in the relative degradative capacity. Why it happens so? Because it happens out of the Monod's equation. After a certain supply of substrate concentration, we do not have any further growth of the microorganisms. Or in other words, if I draw a crude analogy, for suppose if there is a pizza or a burger given to 3 persons, each person has their own maximum capacity to consume. Now, if the food, so far the food available is less than their maximum capacity, the food will be consumed and they will be able to utilize the food for their own growth. But if the availability of food is more than the individual capacity, what will happen? They will use it up to their maximum capacity and rest of the food remain unutilized. So, it will go out of the system as it is without any utilization. It means that if the food supply is more, we are using it at a very high level of consumption, and as the food is less, we are using at very low level of consumption. So, degradative capacity is less when the food is less, degradative capacity is more when the food is more. And but beyond a certain point, further increase will not result in further increase in the degradation capacity. So, from this it appears that if we want to run the plant with 100% degradation capacity, the FYM ratio has to be around 0.7, which means that the microbial population is equal to food divided by 0.7, which means that if the suppose incoming wastewater has a BOD of 500 milligrams per liter, the microbial population should be around 700 milligrams per liter. However, do we really want to operate the plant at 100% degradative capacity? Never, because if we operate the plant at 100% degradative capacity, in that case, if the incoming wastewater has somewhat slightly increase in the BOD supply, then the system will not be able to regulate itself and excess BOD which is coming remain unutilized and become a part of the treated effluent. Therefore, we want to operate the plant somewhere around 50% of its degradation capacity. 50% of the degradation capacity, because if the BOD of the incoming wastewater increases, automatically the system will readjust itself for a higher degradative capacity. Suppose from 500 if the BOD becomes 600, obviously for a given amount of microbial biomass FYM ratio will increase. As the moment FYM ratio increases, it goes with a higher degradative capacity, so excess food is consumed. In case if the BOD decreases from 500 to 400, then FYM ratio decreases, and it decreases so that the relative degradative capacity also decreases and the quality of the effluent remain consistent. That is why we maintain the plant at almost 50% of degradative capacity, which is in case of domestic sewage comes at a 0.3 value, which means suppose if the incoming wastewater has 500 milligrams per liter of BOD, the concentration of the biomass in the system has to be around 1650 milligrams per liter. So, this is how we ascertain the amount of the biomass concentration in the aeration tank. The biomass concentration in the aeration tank is determined by this factor, and self regulation is achieved by maintaining the food to microorganisms ratio or organic sludge loading rate to somewhere around 0.3. In this way, we are able to self regulate the activated sludge process, that is change some fluctuations in the incoming BOD is taken care of, and the effluent which comes out is of relatively consistent quality. Of course, we cannot give a guaranteed quality of the effluent it can vary from 20 milligram to 30 milligram, and there is always some fluctuations in the treated effluent because microbial or bacterial system has its own gestation period. So, broadly speaking, the biomass concentration is ascertained based on the FYM ratio. FYM ratio is fixed so that the system works somewhere around 50% of the degradation capacity, and if we run the system with 50% of the degradative capacity, then it becomes self regulated. This is how the self regulation potential of the activated sludge process is achieved. Now, another point which is important for all of you to understand is how to determine the bacterial biomass concentration in the aeration tank. This bacterial biomass concentration in the aeration tank is determined based on the suspended solid concentration. More reliably, we consider it from the point of view of volatile solid or volatile suspended solid concentration. It is impossible to find out genetically all the organisms and count individually, it is not possible. So, what we do is we take the suspended solid concentration of the aeration tank as an indicator of the bacterial biomass, or more reliably volatile suspended solid concentration of the aeration tank is taken as an indicator of the bacterial biomass. Now, since this bacterial biomass consists of the incoming wastewater as well as recycled sludge all mixed together, it is also known as mixed liquor suspended solids or mixed liquor volatile suspended solids, MLSS or MLVSS. ML is mixed liquor. Mixed liquor denotes the sample is from the aeration tank. Otherwise, it is a suspended solids or volatile suspended solids, which is considered as an indicator of the bacterial biomass of the system. So, to conclude, that activated sludge organisms have the ability to adjust their degraded capacity. Highest buffering capacity relative to quantitative shock loading exists somewhere in the middle of the possible range, because if we work it at around 50% that is middle, then it has a largest buffering capacity for the shock loading, which can be on either increasing side or decreasing side. Short term qualitative changes in the input mass load is transmitted to the effluent, that is from the clarifier there is always some fluctuation in the treated water quality. There cannot be blanket pinpointed one value of the treated effluent. So, this is broadly about the functioning of the activated sludge process. Though the activated sludge process have its own self regulation with respect to the fluctuations in the incoming wastewater, it has also some associated operational problem which encounters in any treatment plant. One of the problem which is associated with activated sludge process is the problem of sludge bulking. I had mentioned you about the problem of sludge bulking when we discussed about the trickling filter advantages and limitations. So, we will discuss now in detail what is a sludge bulking. A bulk sludge is the one that has poor settling characteristics or poor compactability. That is, in a secondary settling tank, the sludge which is coming settles to the bottom. Now, suppose this is one case and the same sludge in a clarifier takes this much volume. What is the difference between these two? Here, to remove the total kg of biomass, we have to withdraw this much volume only, whereas in this particular case, to remove the same amount or same kg of biomass, we have to remove this much volume of from the secondary settling tank. So, this is the condition which is known as sludge bulking. So, a bulk sludge is the one that has poor settling characteristics and poor compactability. There are two principal types of sludge bulking that has been identified. One caused by growth of the filamentous organisms, which is most common cause, and the other caused by the bound water, that is water which is bound with the sludge biomass and that make the entire sludge voluminous. Let me explain you about sludge bulking little more details. Now, here in a secondary settling tank, as I mentioned that the sludge is settling to the bottom. Now, most of these secondary settling tank are made up of RCC and other civil engineering structures, and we cannot exactly see how much volume of the sludge is there at the bottom of the tank. So, we use an index to ascertain the quality of the sludge, and this index is known as sludge volume index, commonly abbreviated as SVI. SVI means sludge volume index. Here what we do, from the aeration tank which is just preceding this clarifier, we take a sample, and for this sample we put it in a cone which is known as in-half cone, and this cone is graduated and appears like this. This is a conical shaped cone which is mounted on a stand and which has a total volume of 1 liter. So, we take 1 liter of water from the aeration tank, put in an in-half cone and allow the solids to settle for about 30 minutes duration. After 30 minutes, we will observe that some volume of the in-off cone is occupied by the settled sludge and remaining portion is a clear supernatant. We measure this ml which is occupied. So, sludge volume index is equal to volume occupied in ml by 1 gram of sludge. So, this is how the sludge volume index is expressed. So, sludge volume index is volume occupied by 1 gram of sludge. Obviously, higher is the value of SVI, more is the volume occupied by the sludge, poor is the quality of the sludge, because we want the sludge to be as compact as possible. For that we want lower values of SVI. So, broadly for the purpose of operation, we consider that if SVI value of any sludge is less than 50 ml, less than or equal to 50 ml, this is a very good quality sludge. If the value of SVI is in the range of 50 to 100, it is called good quality. If it is in the range of 100 to 150, then it is called average quality, and greater than 50, 150, then it is called as bulk sludge. And this bulk sludge is a problem in many of the sewage treatment plant working on activated sludge process. A bulk sludge is the one which occupies more volume in the settling tank. Now, what is the consequences of this bulk sludge? If the sludge is bulky, we need to recycle more volume of the sludge in order to achieve a certain biomass, because we have seen that in activated sludge process we have to recycle a part of the settled sludge back into the aeration tank in order to maintain the biomass concentration expressed in terms of ml VSS. So, we have to recycle. So, if the sludge is bulky, it is occupying more volume. So, to take so much kg of biomass into the system, we have to withdraw more volume. Similarly, this settled sludge has to go to the sludge stabilization unit like anaerobic digester, followed by sludge dewatering volume. So, more volume has to be given there. So, requirement of volume of the anaerobic digester or sludge dewatering system gets increased, which results in either poor efficiency for a given fixed volume pre-designed. So, bulk sludge is a problem, and it caused the problem because of this reason. Now, question comes, why sludge bulking is frequent in a suspended growth system? Now, consider this case that in the aeration tank, what is happening within the aeration tank and within the secondary clarifier, we are actually demanding two contrasting things from the microorganisms. The moment microorganisms are in the aeration tank, we want to have their floating characteristics, that is, they should have less specific gravity, so that they are dispersed throughout the system very uniformly. If they have a very high specific gravity, they will settle to the bottom and it will disturb the system. So, here we want the sludge to be floating in nature. The moment, which is a very small pipeline in between, the moment it enters into a secondary settling tank, we demand that there should be very good settling. So, this is a contrasting feature which we itself wanted from this type of a system. Therefore, the most of the time activated sludge process is operated in such a way that the quality of this bacterial biomass is somewhere between these two extremes, that is, they are neither highly floating nor they are highly compact, and most of the time we maintain the plant in the range of 50 to 100 SVI. So, this is somewhere we want, but under certain conditions beyond our control, we get the situation where the value of sludge volume index suddenly shoots up and sludge becomes bulk. So, let us understand the reasons of the sludge bulking and how to. First reason for sludge bulking is the deficiency of nutrients. The nutrients for the wastewater is nitrogen and phosphorus. Let me explain you in a little bit more detail, because it is a very important concept. How the BOD is removed in a biological treatment system, as I mentioned earlier, the BOD is removed, partially getting converted to CO2, that is carbon is converted to CO2, and remaining part of the BOD is removed as the cell biomass. So, if I denote this as the total kg of the BOD in the wastewater, part of it is converted to CO2 and escape into the atmosphere, and remaining part converted into own cell mass. So, microorganisms synthesize their own cell mass out of the carbon which is there in the wastewater. To synthesize this cell mass, they require nutrient like nitrogen and phosphorus, because a typical cell mass consists of carbon, hydrogen, oxygen, nitrogen, phosphorus and sulfur. These are the main nutrients of any cell synthesis. Carbon is there in the form of BOD, hydrogen and oxygen is always supplied from the water. So, nitrogen and phosphorus are the other essential nutrients for the synthesis of the cell mass. Broadly speaking, if you take a typical cell structure, for every 100 unit of carbon, we require approximately 10 unit of nitrogen and 2 unit of phosphorus. That is, the ratio of carbon is to nitrogen is to phosphorus is 100 is to 10 is to 2. In a biological treatment system which is based on aerobic process, we consider that roughly 50% of the incoming carbon is converted to CO2. So, only 50% is converted to cell synthesis. So, the ratio of BOD is to nitrogen is to phosphorus in a aerobic process is equal to 100 is to 5 is to 1, that is half the requirement, because half is converted to gaseous form. This is the typical ratio of BOD is to nitrogen is to phosphorus. Now, because of some reasons where the excessive dilution of the wastewater has happened, or certain industrial discharge having very high level of BOD, but less level of nitrogen and phosphorus enters into the wastewater, then we have the deficiency of nutrients like nitrogen and phosphorus. That is, we have more BOD as compared to nitrogen and phosphorus dictated by this ratio. In such a situation, the organisms which get developed within the aeration tank are the one which has more surface area. We call these organisms as filamentous organism. These filamentous organisms, they have more surface area, and why these filamentous organisms has a preferential growth over compact organism? Because of their surface area, they are able to compete better for the deficient nitrogen and phosphorus, because whenever there is a deficiency, competition begins. When the competition begins, filamentous organisms has an advantage over the compact organism. As a result, there is a more growth of filamentous organism, and the filamentous organisms results in the sludge bulking, that is, they do not have good settling characteristics. So, one of the reason why the sludge bulking happens is that sometimes we may have deficiency of nutrients like nitrogen and phosphorus. Similarly, suppose there is a prolonged electricity cutoff and the aerators are not working properly, then we may have very low dissolved oxygen in the aeration tank. Low dissolved oxygen again results in the competition between filamentous and compact organism, and it results that the filamentous organism will have preferential growth over the compact organism. Similarly, improper pH, that is either varying or extreme conditions, that is at low pH and excessive large pH, filamentous organisms has a higher generation time, lower generation time as compared to the compact organisms. Widely varying organic loading rate, which means that food supply, if the food supply becomes less or limiting, again the filamentous organisms has the preferential growth. Sulfur is considered to be good for filamentous organisms. So, high influent sulfide concentration also causes filamentous microorganisms, and very low F/M ratio. Low F/M ratio means less food, more microorganisms, which means competition for food. For competition of food, those organisms which has more surface area will have preferential growth over those organisms which has less surface area. So these are the some of the reasons which happens beyond the control of the plant operator in the system, because at times the plant operator may not be having the pre-knowledge of when the wastewater is getting excessively diluted of in terms of nitrogen and phosphorus. There is a prolonged power supply which is beyond his control, okay, variation in the incoming wastewater. These are the some of the things which are beyond plant operator, and sludge, that is why sludge bulking is a problem which is encountered by almost all wastewater treatment plants once in a while. So it keeps on happening, there is nothing, no big deal about it. The point is that suppose sludge bulking happens, first of all we should be able to detect it. Detection means we have to regularly check the sludge volume index of the sludge. The moment the sludge volume index starts exceeding 100 value, that means the problem of sludge bulking is triggering, and at that stage we have to take certain remedial measures. What are the remedial measures for this sludge bulking? First measure is to stop primary settling tank. That is, in a wastewater treatment plant, we know that there is a primary settling tank, followed by aeration tank, followed by secondary settling tank, and this is a kind of a configuration that we have already discussed earlier. So at times if the sludge bulking happens, what we can do, we can bypass the primary settling tank and allow inorganic solids to enter directly into the aeration tank or secondary settling tank, because what will happen that by bypassing primary settling tank, we are allowing some inorganic solids to enter into the secondary settling tank, and these inorganic solids, since they have high specific gravity, they tend to form compact sludge. So for time being, if we just bypass the primary settling tank, then it will reduce the sludge volume index, and the problem can be addressed temporarily if this happens. So this is what we mean that stop primary treatment, that is bypass the primary settling tank. If the sludge bulking cause is detected as deficiency in the nutrient, that is, one should always constantly monitor the incoming BOD value, nitrogen and phosphorus value. If the ratio of BOD is to nitrogen is to phosphorus is in the range of 100:5:1, then there is no problem. But if the ratio is not there, that is, we have less amount of nitrogen and phosphorus for every 100 unit of BOD, it means that there is a nutrient deficiency. In such a case, what we can do is that we can add fertilizer in the aeration tank in order to supplement nitrogen and phosphorus, so as to prevent the preferential growth of filamentous organisms. At times we can make use of controlled use of chlorine, because you may be wondering why chlorine is to be added in a biological system. But by adding a controlled amount of chlorine, what we are doing, we are also preferentially killing the filamentous organisms, because compared to compact organisms, filamentous organisms has more surface area, so they are the one which are likely to die first. So if the system has very high growth of filamentous organisms, we have to inject some chlorine in a controlled manner, so that the filamentous organisms are killed. And finally, we can also think of changing the layout of the system. Now let me explain you this point in a little bit more detail, how the changing of the layout of the system will help. One of the layout of the system is known as CSTR, that is completely stirred type reactor. Other kind of a system is known as PFR, which is known as plug flow reactor. CSTR ideally means that this is a aeration tank, wastewater is entering, wastewater is leaving, we are having very high level of mixing condition, so that the moment the wastewater enters into the system, it gets mixed with the bulk of water. Suppose if S0 is the initial concentration of BOD, SE is the desired disposal standard for the BOD, which is somewhere around 30 milligrams per liter. This is say 300 milligrams per liter. A CSTR system means we have achieved this 30 milligrams within the system itself, because after that secondary settling tank is there which only does the separation of solid, there is no biological degradation which is taking place. So, is ideal CSTR means we are having the complete mixing, and which means that whatever the disposal desired standard is there in terms of soluble BOD has achieved within the system. A plug flow reactor in contrast is somewhat like this, where the BOD of 300 milligram is reduced in a sequence in a plug flow mode slowly, and by the time wastewater comes out of the system it reaches to 30 milligrams per liter. So, this type of a system is known as plug flow reactor, that is, it is moving in a plug flow fashion and the BOD is gradiently removed. Of course, we can never have an ideal CSTR nor we can have an ideal plug flow reactor. What we have in a practice is the reactor which is more near to CSTR or more near to plug flow reactor, and that can be considered as a CSTR or plug flow reactor. Now, suppose if we have these two configurations, so which configuration is better to have more growth of compact organism? It is the plug flow mode, because in a plug flow mode average level of BOD which is food available in the system is somewhere here, that is somewhere around 150 milligrams per liter, whereas in CSTR the average level of food is 30 milligrams per liter. So, in a PFR there is no short supply of food available to the bacteria, and it is the short supply of the food at times results in the growth of the filamentous organisms. Therefore, what we can do is that, suppose this is the aeration tank shown in plan which has some surface aerators, wastewater is entering, wastewater is leaving. What we can do is that we can convert that into a plug flow by putting certain baffle walls in between, so that the flow of water becomes like this. So, this is the flow of water, and a plug flow mode system results in better quality of the sludge. This is what we mean by changing the layout of the system, that is from CSTR mode to a plug flow mode. So, these are some of the methods by which sludge bulking can be reduced. Next comes another problem of the activated sludge process, which is known as rising sludge problem. In this rising sludge problem, in the secondary settling tank we actually see the sludge float on the surface, and this floating of the sludge happens because of the denitrification which happens within the secondary settling tank. Let me explain you this with the help of a diagram. This is a secondary settling tank. Wastewater from the aeration tank is entering. This is the top level of the water. This is the zone of the sludge. Treated water is coming out. This is the sludge recycling line and sludge wasting line. So, this is a typical secondary settling tank of the activated sludge process. Now, here in the secondary settling tank, which has a detention time somewhere around 1.5 to 2 hours. So, what is happening that the sludge which consists of highly active microorganisms, this is activated biomass, goes to the bottom of the tank, and here we generally have no oxygen available. So, in case if the wastewater is nitrified, the moment it enters into the aeration tank is entering, this is the top level of the water, this is the zone of the sludge, treated water is coming out, this is the sludge recycling line and sludge wasting line. So, this is a typical secondary settling tank of the activated sludge process. Now, here in the secondary settling tank, which has a detention time somewhere around 1.5 to 2 hours. So, what is happening that the sludge which consists of highly active microorganisms, this is activated biomass, goes to the bottom of the tank, and here we generally have no oxygen available. So, in case if the wastewater is nitrified, the moment it enters into the aeration tank is entering, this is the top level of the water, This is the zone of the sludge. Treated water is coming out. This is the sludge recycling line and sludge wasting line. So this is a typical secondary settling tank of the activated sludge process. Now here in the secondary settling tank, which has a detention time somewhere around 1.5 to 2 hours. So what is happening that the sludge which consists of highly active microorganisms, this is activated biomass, goes to the bottom of the tank, and here we generally have no oxygen available. So in case if the wastewater is nitrified, the moment it enters into the aeration tank is entering, this is the top level of the water, this is the zone of the sludge, treated water is coming out, this is the sludge recycling line and sludge wasting line. So this is a typical secondary settling tank of the activated sludge process. Now here in the secondary settling tank, which has a detention time somewhere around 1.5 to 2 hours. So what is happening that the sludge which consists of highly active microorganisms, this is activated biomass, goes to the bottom of the tank, and here we generally have no oxygen available. So in case if the wastewater is nitrified, the moment it enters into the aeration tank is entering, this is the top level of the water, this is the zone of the sludge, treated water is coming out, this is the sludge recycling line and sludge wasting line. So this is a typical secondary settling tank of the activated sludge process. Now here in the secondary settling tank, which has a detention time somewhere around 1.5 to 2 hours. So what is happening that the sludge which consists of highly active microorganisms, this is activated biomass, goes to the bottom of the tank, and here we generally have no oxygen available. So in case if the wastewater is nitrified, the moment it enters into the aeration tank is entering, this is the top level of the water, this is the zone of the sludge, treated water is coming out, this is the sludge recycling line and sludge wasting line. So this is a typical secondary settling tank of the activated sludge process. Now here in the secondary settling tank, which has a detention time somewhere around 1.5 to 2 hours. Next comes another problem of the activated sludge process, which is known as rising sludge problem. In this rising sludge problem, in the secondary settling tank, we actually see the sludge float on the surface, and this floating of the sludge happens because of the denitrification which happens within the secondary settling tank. Let me explain you this with the help of a diagram. This is a secondary settling tank. Wastewater from the aeration tank is entering. This is the top level of the water. This is the zone of the sludge. Treated water is coming out. This is the sludge recycling line and sludge wasting line. So this is a typical secondary settling tank of the activated sludge process. Now here in the secondary settling tank, which has a detention time somewhere around 1.5 to 2 hours. So what is happening that the sludge which consists of highly active microorganisms, this is activated biomass, goes to the bottom of the tank, and here we generally have no oxygen available. So in case if the wastewater is nitrified, the moment it enters into the secondary settling tank, there is a tendency that this will start getting denitrified, that is nitrates are converted to nitrogen gas by organisms which are known as denitrifiers under the anaerobic condition. Of course, we will discuss more detail about it in the next lecture, but I am just introducing that under the process where there is a deficit of oxygen, there is a denitrification process which happens and nitrogen gas gets formed. Since nitrogen gas is not soluble in water, what happens, these start forming bubbles of nitrogen, and because of this, these bubbles come to the surface and they carry part of the subtle sludge on the surface itself, which gets conveyed to the treated effluent line. This is what is known as rising sludge problem, that is sludge which has settled rises to the surface and goes out along with the treated effluent. The main cause is denitrification, and we will discuss more in detail in the next lecture. But in case if the rising sludge problem happens, what are the possible solution? The possible solution is the increase the rate of return, that is we have to recycle more amount of the sludge, so that the detention time of the sludge within the sludge zone get reduced, because once the detention time gets reduced, they will not have the chance to get denitrified. So, this is one of the solution. Again, second solution is decreasing the solid retention time by increasing the sludge wasting rate, that is we can waste more sludge, so that SRT get reduced and nitrification will not happen. SRT is something which we have discussed earlier, which is known as solid retention time, and solid retention time is nothing but amount of the biomass in the system, that is kg of biomass in system divided by kg of the biomass wasted. This is equal to volume of the aeration tank into the concentration of the microorganisms divided by the sludge wastage into the concentration of the sludge at the bottom of the aeration tank, that is XR. So, this is how the solid retention time is find out, that is aeration tank, we know the volume of this tank, we know the bacterial biomass, here we know the bacterial concentration in terms of XR. So, SRT is equal to volume into X divided by Q into XR. So, by increasing the sludge wasted, we are increasing the Q, that means we are decreasing the SRT. So, SRT gets reduced by increasing the Q which is wasted out of the system. So, by reducing the SRT, what we are doing, we are not allowing the solids or organisms to remain in the system for long time, that is less SRT means less time for the organisms to stay in the system. Less time means they will not get nitrified, because if you recall while discussing the trickling filter, I had mentioned that nitrifers requires since they have very large generation time, they require the solids to remain in the system for a longer time. So, reducing SRT means reducing the opportunity for the nitrifers to grow. Since nitrifers will not be able to grow, we will not be able have nitrates, and if the nitrates are not there, nitrogen gas will not form in the denitrification. So, this is the some of the possible solution if the rising sludge problem comes. Various types of suspended growth system. These are conventional rate or conventional aeration system, tapered aeration system, step aeration, contact stabilization, extended aeration and oxidation ditches. These are the principal type of suspended growth systems which are used. Only the configuration of the reactor is slightly different under each case, and that is why each of these systems offer its own advantages. So, depending upon the situation, we have to select which the type of system which is most suitable. That is why a fair understanding of each of these types of system is necessary. So, we will take each system one by one. First, conventional aeration. This is nothing but the one we have discussed last time. The conventional activated sludge process consists of an aeration tank. This is an aeration tank, a secondary clarifier. This is a secondary clarifier, a sludge recycling line. This is the sludge recycling line, sludge wasting line. This is the sludge wasting line. Wasting means it is going to the anaerobic digestion for further biological stabilization or sludge dewatering unit. And both effluent, that is the settled wastewater after primary settling tank, and the recycled sludge enters the head end of the aeration tank, and here the entire system is aerated for about 6 to 8 hours of duration. That is, recycled settled sludge and the wastewater from primary settling tank are mixed together in a mixed liquor and aerated for 6 to 8 hours. The influent wastewater and recycled sludge are mixed by action of diffused aerator or mechanical aerator. Diffused aerator is the one which you have seen in the fish aquariums, where there are diffusers which are attached, which bubbles the air, and these diffusers are connected to a compressor which sucks the atmospheric air and supply it to these diffusers under pressure conditions, so that the air comes in the system like a bubble and creates mixing. Or many a times we use mechanical aerators, most of which are surface aerators, which are mounted on the surface and they rotate at a very high speed, creating turbulence of the water, which helps in the mixing as well as aeration of the mixed liquor. So, during this period of aeration, adsorption, flocculation and oxidation of organic matter takes place. The mixed liquor is settled in the activated sludge settling tank. So, this mixed liquor goes to the settling tank and this is settled over here, and the sludge is returned back into the system, which is approximately 25 to 50% by ratio of the incoming flow rate. Of course, in the last lecture we had discussed how to know the quantity of the sludge to be returned back for a given concentration of BOD of the wastewater, that is to achieve a particular F by M ratio. So, one continuously monitors ml VSS concentration, compare it with the desired level of VLS concentration, find out the value of SVI, and based on this one can estimate how much quantity is to be returned back into the system, which generally is found to be in the range of 25 to 50%. So, this is a conventional aeration system which we have discussed in much more detail last time also. First, conventional aeration, this is nothing but the one we have discussed last time. The conventional activated sludge process consists of an aeration tank. This is an aeration tank, a secondary clarifier, this is a secondary clarifier, a sludge recycling line, this is the sludge recycling line, sludge wasting line, this is the sludge wasting line. Wasting means it is going to the anaerobic digestion for further biological stabilization or sludge dewatering unit. And both influent, that is the settled wastewater after primary settling tank, and the recycled sludge enters the head end of the aeration tank, and here the entire system is aerated for about 6 to 8 hours of duration. That is, recycled settled sludge and the wastewater from primary settling tank are mixed together in a mixed liquor and aerated for 6 to 8 hours. The influent wastewater and recycled sludge are mixed by action of diffused aerator or mechanical aerator. Diffused aerator is the one which you have seen in the fish aquariums, where there are diffusers which are attached, which bubbles the air, and these diffusers are connected to a compressor which sucks the atmospheric air and supply it to these diffusers under pressure conditions, so that the air comes in the system like a bubble and creates mixing. Or many a times we use mechanical aerators, most of which are surface aerators, which are mounted on the surface and they rotate at a very high speed, creating turbulence of the water, which helps in the mixing as well as aeration of the mixed liquor. So, during this period of aeration, adsorption, flocculation and oxidation of organic matter takes place. The mixed liquor is settled in the activated sludge settling tank. So, this mixed liquor goes to the settling tank and this is settled over here, and the sludge is returned back into the system, which is approximately 25 to 50% by ratio of the incoming flow rate. Of course, in the last lecture we had discussed how to know the quantity of the sludge to be returned back for a given concentration of BOD of the wastewater, that is to achieve a particular F by M ratio. So, one continuously monitors ml VSS concentration, compare it with the desired level of VLS concentration, find out the value of SVI, and based on this one can estimate how much quantity is to be returned back into the system, which generally is found to be in the range of 25 to 50%. So, this is a conventional aeration system which we have discussed in much more detail last time also. Next comes the tapered aeration system. If you look at in the conventional system which we have just discussed, the one of the thing which comes out very prominently is that here the wastewater and mixed liquor enters simultaneously at one end of the or head end of the tank. Now, suppose initially the BOD is 300 milligrams per liter. So, what we have is that by the time wastewater leaves, the BOD reaches to the disposal standard of 30 milligrams per liter. I am talking in terms of soluble BOD. That is, the BOD is decreasing linearly from this end to this end. So, obviously, when the initial portion of the aeration tank has activated sludge coming into the system as well as the fresh wastewater. So, here the biological activity is likely to be very high, that is the rate of consumption of oxygen is much higher as compared to the later portion of the tank where the BOD itself is low. Therefore, the oxygen, there is a different oxygen requirement in different sections of the aeration tank, and this is what we mean by tapered aeration, that is we give very high level of oxygen supply in the initial stages and the oxygen supply proportionally reduces as we move ahead in the aeration tank. So, this is what is known as tapered aeration. Therefore, the objective of tapered aeration is to match the quantity of air supplied to the demand exerted by the microorganisms. As the mixed liquor traverses the aeration tank, the tapered aeration affects only the in terms of arrangement of diffusers. That is, how do we achieve the tapered aeration? Initially we have more diffusers, and as we go down the spacing or the number of diffusers reduces. So, this is how we achieve the tapered aeration. So, in the tapered aeration basically means arrangement of diffusers in the aeration tank and the amount of air consumed. At the inlet of the aeration tank, where the requirement of oxygen is high, we have more number of diffusers, and at the later end we have less number of diffusers. This results in low F by M ratio, because what happens when we go ahead, the food initially is high, microbial population is also high. As we go down, what happens? The food decreases. So, F by M ratio decreases. So, it lowers the F by M ratio and lowering the oxygen demand altogether at the lower end. The spacing of diffuser is thus increased towards the tank outlet to reduce the oxygenation rate. So, this results in two beneficial effects. First, reduced oxygenation means less air is required. This reduces the size of the compressor or air blower which is provided and the overall operating cost. And secondly, we are avoiding over aeration, and by avoiding over aeration we are limiting the growth of nitrifying organisms, because these nitrifying organisms exert more oxygen demand and it also result in the denitrification or sludge rising problem in the secondary settling tank. So, this is the basic advantage of tapered aeration, that is operating cost reduces, oxygen utilization is more efficient and the sludge rising problem is reduced because we are not allowing the nitrification to take place. So, in a tapered aeration we are providing very briefly, we are providing more oxygen where it is required more, we are providing less oxygen where it is required less. This is what it means tapered aeration, and we achieve it by changing the spacing between the diffusers, that is more number of diffusers initially and less number of diffusers at a later stage. Then comes step aeration. Step aeration is a modification over the tapered aeration. In the step aeration process, what we do is the activated sludge, it is actually a activated sludge process in which the wastewater coming from primary settling tank is introduced at several parts of the tank. So, suppose this is the aeration tank. So, we are allowing the inlet water at various locations in the aeration tank itself. So, this is what it means, that at several parts of the aeration tank. This helps to equalize the F/m ratio. That is, what we are doing is that we are maintaining constant F/m ratio in each section of the aeration tank, and this lowers the peak oxygen demand also. That is, since we had equally distributed the incoming wastewater, that is kg of BOD coming per day is equally distributed throughout the tank. So, oxygen demand is also constant throughout, that is there is no variation in the oxygen demand. Like in a conventional aeration, more oxygen demand is in the initial stages and less oxygen demand is in the later stages. But in the step aeration, oxygen demand, F/m ratio, everything is constant throughout the tank. So, here aeration tank is divided into 4 number of parallel channels through the use of baffles. So, practically speaking, what we do, we introduce, this is, suppose this is the layout or plan of the aeration tank. We introduce baffles in the aeration tank and we introduced the wastewater at various sections like this. That is, aeration tank is divided into 4 or more number of parallel channels through the use of baffles. Return activated sludge also enters in the first step of the aeration. So, after this, the wastewater goes to the secondary settling tank, from where we are returning, and this is returned to the first unit of the step aeration. So, return activated sludge enters the first step of the aeration tank along with the portion of the settled wastewater. Here the piping is so arranged that an increment of wastewater is introduced in the aeration tank at each step. So, this is done through the various piping arrangements. If desired, the first step can be used for re-aeration of the returned activated sludge alone. So, at times we do not introduce any incoming wastewater in the first tank, but the first portion of the aeration tank is only used for aeration of the returned sludge only. So, this if it requires, it can be used for this. So, basically the step aeration provides enough flexibility of operation, which is one of the important feature of this process. In step aeration, however, the oxygen demand is more uniformly spread over the entire length of the aeration tank, resulting in better utilization of oxygen supply. So, we are not wasting oxygen supply anywhere because it is evenly distributed and it is therefore efficiently utilized. Multiple point introduction of wastewater maintains an activated sludge with high absorptive properties. So, as you know that absorptive property of a flock reduces as it is exposed to more food. If I draw a crude analogy, if food is available to a one person, initially it will consume more if he is hungry, later on. Next comes contact stabilization. The layout plan of a contact stabilization is like this. That is, we are dividing the tank broadly into 2 stages. First is the sludge re-aeration tank and the other one is known as contact tank. So, what we are doing is that we are just partitioning the aeration tank into 2. this is our secondary clarifier from where we are wasting the sludge and returning the tank. So, this is the layout plan of a contact stabilization. The contact stabilization process was developed to take advantage of the absorptive properties of the activated sludge. It has been postulated that BOD removal occurs in two stages in the activated sludge process. The first stage is the absorptive phase, which requires about 20 to 40 minutes time. So, 20 to 40 minutes time is required for the absorptive phase. During this phase, most of the colloidal finely suspended and dissolved organics are absorbed in the activated sludge. The second phase, which is oxidation phase, occurs and the absorbed organics are assimilated metabolically. So, this is, if you recall, we have adsorption, absorption and assimilation, dissimilation. So, what we have seen is that absorption takes about 20 to 40 minutes time, and then significant amount of the time requires for its assimilation and dissimilation. In the activated sludge process, which we have discussed earlier, these two processes occur in the same tank, but in the contact stabilization process, the two phases are separated and occur in the different tanks. That is, we are having mainly the absorption here and assimilation dissimilation process happening in this tank. The settled wastewater is mixed with the re-aerated activated sludge and aerated in the contact time for about 30 to 40 minutes. During this period, organics are absorbed by the sludge flocks, and the sludge is then separated from the treated effluent by sedimentation and returned into the sludge re-aeration tank, where it is aerated for 3 to 6 hours in a sludge aeration tank. During this period, the absorbed organics are used for energy and production of new cells. A portion of the returned sludge is wasted prior to recycle to maintain a constant ml/VSS concentration in the tank. The aeration volume requirements are approximately 50% to that what we have for the conventional or tapered aeration plant. It is thus often possible to double the plant capacity of an existing conventional plant by just simply doing some retrofittation in this form, which is shown as a layout plan. The redesign may require only changes of pipeline and some minor changes as shown. So, a normal aeration tank which is being used earlier, suppose if we are having increased amount of the wastewater flow or increased loading of the thing, what we simply do is that rather than wastewater coming like this, we change the piping layout, cut this off, put it here, contact time which is about 30 minutes to 90 minutes duration, and rest of the aeration tank is 3 to 6 hours, which is for the sludge re-aeration. And here in the sludge re-aeration, mainly assimilation and dissimilation taking place, here absorption is taking place. This is secondary settling tank. So, by simply changing, we are converting a conventional aeration tank into a contact stabilization tank, which improves the efficiency of the overall process, or it can handle the increased organic loading. Next comes extended aeration system. The extended aeration process operates in the endogenous respiration phase of the growth curve, which necessitates a relatively low organic loading and long aeration time. Here I want to mention about the respiration phases of the organisms. If I plot a graph between contact time versus mass of microorganisms, then the growth of microorganisms follows this type of a shape. In this, what we say, initially there what is known as lag phase, LAG, lag phase. Lag phase is the one in which organisms for a given amount of time do not grow at a fast pace. This is actually the process of what is known as acclimatization, where organisms are trying to acclimatize themselves to the new environmental conditions, and for organisms these environment conditions are pH, temperature, salt balance of the water, as well as the food available. So this is a kind of an acclimatization phase where for a given amount of contact time there is not much significant increase in the microorganisms population. Then comes a stage where the growth of the organisms is very fast, and this is known as exponential growth phase. Exponential growth phase is the one where organisms start multiplying at a very fast rate. Then comes the declining growth phase, in which organisms are growing, but the growth rate is not same as it was in the previous stages. So it is growing at a declining phase. Then comes a phase which is almost can be called as a stationary phase, that is, there is no net growth of the organisms. Then comes a stage in which the organisms are more in number, but there is no adequate supply of the food or substrate. This is the stage in which the organisms start consuming their own cell mass, and this is known as endogenous phase. So broadly speaking, what is happening, the conventional high rate aeration works in this phase of exponential growth phase or up to part of the declining growth phase. So this is what we have discussed, the activated sludge process so far. In the extended aeration process, we are talking of that we are doing the aeration till the endogenous growth phase of the organisms. That is, we are allowing the contact time to such a duration that they go up to the endogenous phase. That is why I am repeating my statement which I had just mentioned, that the extended aeration process operates in the endogenous phase of the growth curve, which necessitates a relatively long aeration time and low organic loading. That is, organic sludge loading rate or F/M ratio here is less than or equal to 0.15 as against approximately 0.3 in a conventional activated sludge process, which we have discussed in the last lecture. This process of extended aeration is extensively used for packaged sewage treatment plants, and they are provided for treatment of waste from housing, colonies, societies, schools, community and all. Because the main advantage of this process is that since the organisms has already gone up to the endogenous phase, we do not require sludge stabilization, that is sludge which is being wasted after the secondary settling tank. This sludge in a normal process goes further stabilization in an anaerobic digester or any other biological treatment system. But when we go for the extended aeration system, we do not require further sludge stabilization because organisms have already stabilized within the system. Therefore, what happens for small communities when the flow rate is not high, it is better to provide long duration aeration time, because aeration can be given even for 24 to 30 hours, will not result much of the increase in the volume, but avoiding additional unit will be of much advantage. So in fact, the aeration process is only a modification of the activated sludge process and consists of an aeration tank followed by a clarifier and a recycle line. So the entire system is same as we have discussed in a activated sludge process. Only difference is that here the detention time is about 22 to 30 hours, F/M ratio is low, and we do not require further sludge stabilization. So broadly speaking, in this process a long retention time and low F/M ratio capitalizes the microbial activity up to their endogenous growth phase. The biological mass which is synthesized at a declining growth phase is oxidized by the microorganisms itself. Therefore, the biomass synthesized at the declining growth phase contains a small fraction which is not biodegradable and accumulates as sludge in the system. The excess sludge thus produced is highly stable and can be directly dried over a sludge drying bed. So, here we can supply it directly to the sludge drying bed. This process eliminates the sludge digestion arrangement, and the primary settling tank is also often eliminated in the treatment system, because we can directly, in a small sewage treatment plant for a small community, we can directly have screen chamber followed by grid chamber followed by extended aeration process, and that is a very simple treatment which we can use. So, this is how a small package sewage treatment plant can be provided with the use of extended aeration. Next comes oxidation ditches. This is also used for small community sewage treatment. Here we have inlet. This is the inlet of the wastewater. This is the outlet of the wastewater. This is a circular chamber where we had provided some rotor, so that water keeps on circulating in this tank, and we provide aerators also at times. So, oxidation ditches are simple artificial ditches dug in the ground for the purification of sewage using a very simplified technique. The basic form of the plant is a ring shaped circuit or ditch. Across the length of the ditch, an aeration rotor is mounted. This is the aeration rotor which can be mounted, which provides oxygenation as well as circulation of sewage in this manner. Oxidation ditch can be intermittent or continuous. For intermittent operation, cycle consists of closing of the inlet valve and aerating the wastewater, stopping the rotor itself and letting the contents to settle, and opening both inlet and outlet valves, thereby allowing the incoming wastewater to displace the equal volume of the clarified effluent. So, it can be operated on a continuous as well as intermittent mode by operating the valves as I just mentioned. So, this is about the oxidation ditch, and these are the principal types of modifications of activated sludge process which we can use. So, this finishes the discussion on the types of suspended growth system. We will come to the important topic of biological nitrification and denitrification. Domestic sewage also contains nitrogen in it, and we have seen that if the nitrogen is allowed to be discharged in the wastewater to the ambient water bodies, it results its own negative impact, principally in the form of growth of excessive amount of algae, which is known as eutrophication, which has its own negative impact on the receiving water body. We have seen or discussed that in much details in one of the previous lecture. So, one of the objective of the sewage treatment other than that of removal of organic matter in the form of BOD is to remove nitrogen from the water. And the process of removing nitrogen from the water, we have seen there is a chemical methods which we generally don't use for the sewage, but use for the industrial discharges. And if you recall, we have discussed these method like breakpoint chlorination, ammonia stripping and so on. But we also have the biological method by which we can remove nitrogen, and the process is principally known as nitrification followed by denitrification. Let me take you again from the fundamental concept, and this concept we had discussed earlier in the context of sludge bulking, that for biological, in the case of biological treatment, for each 100 unit of BOD we require 5 unit of nitrogen and approximately 1 unit of phosphorus if the process of treatment is aerobic. So, in the aerobic treatment process, BOD is to nitrogen is to phosphorus ratio is 100:5:1. This ratio is from the concept that the BOD, that is organisms synthesize the cell mass, and during the synthesis of cell mass they uptake about nitrogen and phosphorus in this ratio, and this uptake of nitrogen, phosphorus and synthesis of cell mass results in formation of settleable flux, which gets separated in the secondary settling tank, and finally waste goes out of the system as the sludge solids. So, a part of the total nitrogen coming in the wastewater is removed by the normal activated sludge process in the form of synthesis of cell. To give you an example, suppose if the sewage has 300 milligrams per liter as a BOD and we are reducing up to, or say 330 milligrams of BOD initially, and we are reducing to the discharge standard of say 30 milligram per liter of BOD, that means we have reduced 300 milligram of the BOD per liter, and converting into we can convert in terms of kgs per day. So, by multiplying this by discharge. So, basically for 300 units of BOD, what we can say is that 15 milligrams per liter of nitrogen is already taken care of in terms of the synthesized cell mass out of this BOD. That is, for every 100 unit 5 unit is there, therefore, for 300 unit 15 unit of nitrogen is synthesized as cell mass, separated in the secondary clarifier and wasted out of the system. So, this is how some part of the nitrogen is removed, but a major part of the nitrogen, in case if it is highly nitrified water or the sewage has excess amount of nitrogen, then we have to go for special treatment for the removal of excess nitrogen. This treatment follows basically 2 steps. First step is the nitrification, wherein we convert nitrogen in the form of, which is present mostly in the form of ammonia, into nitrite and nitrates, that is, this is known as nitrification. And finally, what we do is that we convert nitrates into nitrogen gas. This process is known as denitrification. So, it is a 2-step process. So, let me first explain you about the principles of nitrification, and then later on I will discuss with you the principles of denitrification. So, I am starting the discussion on the principles of nitrification. For the purpose of biological treatment, we have 2 types of organisms: autotrophic organisms and heterotrophic organisms. Heterotrophic organisms are those which consumes organic matter as food, which we call as substrate. Autotrophic organisms are those which depends upon inorganic compounds for as a source of their energy. So, nitrogen, if present in the sewage, certain amount of nitrogen is required for the growth of organisms. So, the steps which goes in the nitrification is ammonium nitrogen is first converted by set of autotrophic organisms known as nitrosomonas. So, nitrosomonas convert ammonium nitrogen into nitrites. Then comes the next step, where nitrites are converted by another set of organisms, autotrophic organisms, which are known as Nitrobacter. So, Nitrobacter converts nitrites into nitrates. So, the net reaction of these 2-step process is nitrogen present in the form of ammonium compounds is finally converted to nitrates in this. So, this total reaction or this process of conversion of ammonia into nitrate is known as nitrification, which is achieved by 2 sets of autotrophic organisms, Nitrosomonas and Nitrobacter. However, the process of nitrification is a slow process as compared to the process of degradation of organic matter. Nitrification process is a much slower process. Why the nitrification is a slow process? Because we have to understand this concept, since if we are intending to design our treatment system for the purpose of removal of nitrogen, we have to consider the basic understanding how we can achieve nitrification, and then later on how to achieve denitrification. But prior to that, let us understand that nitrification is a slow process. It requires special consideration because of its slow growth. So, question now we will discuss why nitrification is a slow process. First reason why it is a slow process is the generation time of nitrifers. They have long generation time, that is they multiply at a slow rate, that is the time required for multiplication is much more. So, the growth rate of the nitrosonomas is nitrifers is less. Why it is less? Because growth of any organisms depend upon how much amount of net gainful energy the organism derives from its food. Suppose if we consume the food which is rich in calories and thing, we have more body weight. At times humans become obese also by consuming highly energy food. Same way, if organisms are able to drive more energy out of the food, they increase their biomass faster, and heterotrophic organisms gain much useful energy out of the organic matter in comparison to autotrophic organisms which depends upon these type of inorganic compounds. Why it is so? Because in the organic matter hydrogen is loosely bound. So, the amount of energy to be expended to break down the to cleave the hydrogen from the organic matter for the purpose of oxidation is much less in case of organic matter as compared to the inorganic matter, because here the bond energy of hydrogen is much more. So, the net energy gain in case of inorganic compound is less as compared to the organic compounds. This results in the slow growth rate of nitrifers, nitrosonomas and nitrobacters. This is one of the reason why it is slow. Second, this is a series step, that is if you compare with the organic matter, there are different sets of organisms which are working parallelly: yeast, fungi, bacteria, rotifers, protozoa, so on, and variety of organisms are working parallelly on the organic matter for its degradation. Whereas, in case of conversion of ammonia into nitrates, it is a step process, that is first a peculiar set of organisms known as nitrosonomas has to convert into nitrites. Unless sufficient amount of nitrite is available as food for the nitrobacter, because for nitrobacter the food is nitrite here. So, unless sufficient amount of nitrite is produced by the nitrosomonas, nitrobacter will not start growing. So, first nitrosomonas has to grow to produce sufficient amount of nitrites, and then nitrobacter can convert nitrites into nitrates. So, it is a step process, two-step process. So, that is another reason why the process of nitrification is slow as compared to degradation of organic matter. The third reason is that there is a drop in pH because of the formation of free hydrogen radical. The drop in pH results in that unless the water has sufficient alkalinity as for the buffering of the drop in pH, the conditions for the growth of these will not be available to an optimum level. So, that is the third reason why the nitrification is a slow process, and the fourth reason is that it requires high level of oxygen. So, we need to supply excess amount of oxygen into the system for this process to happen. So, these are the reasons why the nitrification is a slow process, but now we will discuss it the other way around. We want nitrification to happen. So, let us understand what are the conditions which are required for nitrification to happen, and it comes from the simple reason that we have to provide all those conditions for the nitrification so that they can grow and do their function properly. So, for the nitrification, the first condition is supply excess amount of oxygen. Second condition is that provide sufficient amount of alkalinity. The third condition is that detention time has to be increased, and here detention time is not that of hydraulic, that is for water, but it is for the solid. So, we have to increase the solid detention time, because the nitrifers itself has a low generation very high generation time, that is for organisms to grow in sufficient quantity, it has to remain in the system for a longer time. That is why when we discuss about the trickling filter, since in the trickling filter the lower layer of the trickling filter has less growth of the slime layer. So, they are also removed in a very long time. That is why the nitrifers are able to grow in the lower layers of the trickling filter. Similarly, in the suspended growth system we have to provide very high solid retention time. Now, question comes, how to increase the solid retention time? Solid retention time can be increased by maintaining low FYM ratio or organic sludge loading rate. So, this has to be less than or equal to 0.15 kg of BOD per kg of ml/VSS per day. So, if we are able to maintain the organic sludge loading rate less than this level, then only SRT will be high. Now, question comes, why I am correlating FYM ratio with SRT? Broadly, the relationship between the sludge age versus organic sludge loading rate is like this. That is, as we keep on increasing the organic sludge loading rate, we are decreasing the sludge age or solid retention time. So, this solid retention time keeps on decreasing. Therefore, if we are able to maintain less than 0.15, then we are able to achieve SRT greater than 20 days. So, therefore, this is the necessary condition for the nitrification to happen. Normally, the generation time of nitrifers is also temperature dependent. At 10 degrees centigrade, the generation time is approximately 3.4 days. At 20 degrees centigrade, the generation time is approximately 1.32 days. At 30 degrees centigrade, the generation time is approximately 0.53 days. So, as the temperature increases, the generation time reduces, and that is why the problem of nitrification is more often in the summer conditions. And since the wastewater get nitrified, we have the rising sludge problem in the secondary settling tank more during the summer regions. This is the reason in the last lecture when I discussed about rising sludge problem, I had mentioned about it. So, these are the conditions based on which we can achieve the nitrification within the conventional activated sludge process, if we are able to maintain or operate the plant at low organic sludge loading rate and able to provide excess amount of oxygen. Then comes our next step, that is denitrification. Once we are able to produce nitrates, these nitrates ultimately has to be converted to nitrogen gas. This process is known as denitrification. The exact step or reaction for the denitrification is like this. We are converted to nitrogen. Now, here what is happening is, if the organisms do not have oxygen, then in order to achieve their respiration, they will try to cleave oxygen or get oxygen from these type of inorganic compounds. And therefore, once they cleave the oxygen from these inorganic compounds, then what we get is the nitrogen gas. And we know that nitrogen is insoluble in water, so it immediately escapes into the atmosphere. So, the requirements for the denitrification is that first of all we should have sufficient amount of organic matter, because unless organic matter is present, then only the organisms will try to oxidize the organic matter and they will exert oxygen demand. So, organic matter has to be present in the system so as to so that organisms will demand oxygen. And secondly, the condition has to be anaerobic, that is absence of air, because in the presence of atmospheric air which gets dissolved in the water, the oxygen demand will always be met through the least energy route of the organisms, that is they will take the atmospheric or dissolved oxygen. But if the water does not have any dissolved oxygen and it is cut off from the atmosphere also to replenish that is under anaerobic condition, then organisms do not have any choice but to cleave oxygen out of these nitrite or nitrates. So, the necessary condition for this reaction to take place, that is denitrification, is the presence of anaerobic condition. So, normally what we do is that for the purpose of denitrification, what we can do is we have to provide an aeration tank which is operating at low F/M ratio. Then we have to provide a denitrification tank Then we have to provide a secondary settling tank, and rest of the system remains same as we have discussed earlier. Okay. So, this is denitrification tank. This is what the common wisdom says, that to provide this, first of all we are nitrifying. Here what we are doing, we are converting ammonia to nitrates, and here we are converting nitrate into nitrogen gas to escape. So, this is what the basic concept is, but practically we do not do in this way. So, the practical application for denitrification in the activated sludge process is somewhat different. Here what we do is we first provide denitrification tank, that is normal aeration tank is converted into denitrification tank initially, followed by nitrification tank, which is normal aeration tank. Wastewater is coming here, and the system operates the way it was discussed earlier. Now, see, in the earlier slide I had shown you the aeration tank followed by denitrification tank. Here in this slide I am saying first provide denitrification tank and then provide aeration tank. So, this why it is so? It is so because in the earlier configuration we are not able to provide food in the denitrification tank. Now, suppose if I redraw this configuration here, this is the aeration tank, this is the denitrification tank, secondary settling tank, and this. So, aeration tank, denitrification tank. So, here since in the aeration tank we had already converted initial BOD to the near to the disposal standard of 30. So, almost negligible amount of food is available at this stage. If the food is less, obviously the organisms will not exert oxygen demand because the food is not there. For to do that, we have to put part of the untreated water directly into the denitrification tank, so that sufficient amount of organic matter is available for the organisms. But it is not easy because we cannot mathematically predict the exact nature of degradation of the bypassed sewage here, and we cannot be sure of the consistent quality of the BOD in the treated wastewater. This is one of the problem of the normal way of thinking of the denitrification system. Second problem with this system is that in the denitrification we always get 2.5 moles of oxygen, and this release of oxygen by the denitrification can offset the moles of oxygen required for the nitrification step. So, the net amount of oxygen required for in the coupling of nitrification denitrification is only 2.1, but in this case we have to already supply excess of 4.6 moles of oxygen, and whatever oxygen in this process is released is not utilized. Whereas, by doing the process in this way we are able to provide sufficient amount of food in the denitrification tank, we can be sure of the consistent quality, as well as we are able to utilize the oxygen which is released as the process of denitrification in the aeration tank. So, the overall oxygen requirement get reduced. So, this is why the configuration or practical application of nitrification denitrification is incoming wastewater and recycled sludge all together are introduced in the first tank, which is non aerated under anaerobic condition, which is known as denitrification tank, and from here the wastewater goes into the aeration tank where the things are getting nitrified and the sludge is separated, and this is how the system is operated for the biological removal of the sewage. Then we have some other types of working of the thing. I had mentioned about CSTR and the plug flow reactor. CSTR is the completely stirred reactor, and plug flow reactor is the one in which the mode of the flow is in a plug fashion, that is it getting replaced. CSTR typically is represented by this symbol. So, in terms of efficiency, plug flow reactor is more efficient as compared to CSTR reactor, because in the plug flow reactor more food is available at a given point, and since more food is available, from the Monod's graph we have seen that more is the specific growth rate of the organisms. That is why plug flow reactor is more efficient as compared to the CSTR type of reactor. So, with this we had finished the discussion on the suspended growth system, and also we have finished the discussion on aerobic based treatment technologies. We have discussed about the attached growth system, suspended growth system, various modifications of the suspended growth system, its advantages, limitations, problems that we faced, that common operational problems, as well as how to remove nitrogen by the biological treatment systems. Thank you.